Welcome back. So in this class, let us study the ARM core fundamentals. So that is data flow model and the register file of R, CPSR register, bank register concept, and pipelining architecture. So a diagram shows the data flow model of R. So it has got many functional unit in it. The arrays are nothing but a data bus here, and blocks are performing a specific functionality. Now, the main blocks in this data flow model are instruction decoder, sign extend, register file, barrel shifter, ALU, MAC, address register, and incrementer. So the ARM implements in a Van Neumann architecture. So Van Neumann architecture means both data and instructions are bought in the same bus. So that is a Van Neumann architecture. Whereas in the another type of architecture is Harvard architecture, in which both data and instruction will have a separate buses. So this ARM is implementing a Van Neumann architecture. So data and instruction are brought through data bus. So once the instruction are brought, the instructions are sent to instruction decoder. So wherein it translates those instructions. So it gets the meaning of that particular instruction and tells ALU what needs to be done. So instruction just translate those instructions. And there is one more block, that is sign extend, which converts the instruction from 16 or 8-bit into 32-bit instruction. So thereby it is preserving the sign of the particular data. So once the data are read from the memory, they are stored in the register file. So register file is a bank of registers. So it will have many registers. So altogether there are 37 registers, and some of them are hidden during the execution. We will come to that in the later part. So storage bank of ARM is register file, and from these register file, ALU takes the data. So it has got two registers, source registers, those are RN and RM, and one destination register RD. The data from the register file enters to ALU through internal bus, those are A and B. And it has got one important functional block, that is barrel shifter, which is placed between a register file and ALU. So this particular hardware pre-processes one of the operand before it enters to ALU. So before the data from the bus B will go to a barrel shifter, and once after processing in the barrel shifter, it is sent to ALU. So before entering into ALU, one data gets pre-processed. So that increases the scalability of ARM instructions. And after this, the data are sent to ALU. So ALU stands for arithmetical logical unit. So which performs most of the functions are performed by this ALU. So like addition, subtraction, logical functions like and, or, all those things are done in this ALU. There is one more functional unit that is called as MAC, multiply and accumulate. So this particular hardware is useful for or is used for handling multiplications. It takes care of all signed and unsigned 32, 64-bit multiplications, and both ALU and MAC calculate these or perform the operations and place the result onto the register RD. Through this bus, they will place the result back into register file. Address register and incrementer together, they will calculate the next instruction in case of sequential memory access. Say we are accessing an array, so every time the pointer has to point to next data allocation, and the address is held by address register, and incrementation has taken care by this incrementer block. uh, so this is what we discussed till now. That is the decoder translates, and so load and store architecture are used. So load and store architecture means, so load instruction will load the data from memory to into register, and store instruction will store the data from register to memory. So there is a register file which is the storage bank. With all the registers are 32-bit, and two source registers, that is Rn and Rm, and a single destination register RD, and operands are read from buses A and B. So ALU and MAC performs many operations, takes RM and RM from A and B and computes the result, and data processing instructions write the result into register file. Load and store instructions uses AL to generate the addresses. So RM can be pre-processed in the barrel shifter. So that's what I already told. So barrel shifter pre-processes one of the operand before entering into ALU. For load and store instruction, incrementer and address register are used for updating the address of a sequential memory access. So processor continues to execute in the normal mode until and unless an exception is raised. So the next important concept is register file of ARM. So registers are used for holding data and addresses. So in the ARM, registers are identified by a small letter R prefixed to a register number. For example, if the register number 4 will reference it as R4. So R is a small letter that is used for identification of registers. All the registers that are available in the ARM are 32-bit in size. At any time, 18 active registers are there. So at any time, 18 registers will be active. Other registers will be hidden from the programmer. So among that 18 registers, 16 are data registers and 2 are processor status registers. So from R0 to R12 are purely general purpose registers, and 3 registers, that is R13, R14 and R15, have got some special functionality. So those can also be used as general purpose, provided it's not being used for the functionality which is meant for it. So R13 has got a special functionality, that is it is a stack pointer. So what is the work of stack pointer? It points to the head of the stack or top of the stack. R14 is the link register, so which stores the return address whenever it calls in subroutine. So whenever an ARM processor calls subroutine, so before jumping into subroutine, it stores the return or where to return. So that address is stored into LR. And R15 is program counter. So program counter will always be pointing to the next executable instruction. I already told that is registers R13 and R14 can also be used as general purpose, but you should not be using stack, or you should not be using subroutine. So in those cases, you can use R13 and R14 also as a general purpose registers. R0 to R13, all the registers are orthogonal. So orthogonal means any instruction which can be applicable to R0 is equally applicable to register R13 as well. So that means to say any instruction can use any register. That's what is orthogonal meant. The two program status registers are, one is CPSR, another one is SPSR. CPSR stands for current program status register, while SPSR stands for saved program status register. So we'll see them in the next coming slides. So CPSR stands for current program status register. So this particular register stores the information about the our processor, like which all flags have been raised, and whether the processor is in which mode, interrupts have been masked or not, or whether it is in the thumb mode, like that. So all this information is stored in the CPSR. The CPSR structure is divided into four fields, each are 8-bit. So we can read out in the top, there is flags, status, extension, and control. So these are the fields in the CPSR. So at present we are not using status and extension, but we are using flags and control. So the control field has got processor modes, processor states, that is ARM state or thumb state, and interrupt mask bits, that is I and F bit, the interrupt mask bits. In the flags field contain conditional flags like negative, zero, carry, and overflows in ZCB flags. So these flags are generated in the data processing instructions. So now let us see in detail what these flags meant for, and what it stores. So the bit number 31, so here in the leftmost column reads the bit number, and the next column reads the bit in the CPSR. That is, bit means the meaning of that bit, and then what is the meaning of that particular flag or anything. So the first one is, the bit number 31 is N, stands for negative flag. So this negative flag tells whether the number is signed or unsigned number. So if MSB is 1, that means the number is a negative number. MS means 31st bit of the data. So if that is equal to 1, that number is treated as negative, and if it is 0, it is treated as positive. And this is very helpful in the signed operations. The bit number 30 of CPSR is 0 flag, represented by Z. So 0 flag indicates that the last operations, ALU operation, has resulted in 0. So if it is equal to Z, if Z is equal to 1, that means to say last operation has resulted in 0. And if it is equal to Z flag equal to 0, means last operation hasn't resulted in 0 result. That means so a result is non-zero. The next bit, that is 29th bit, is carry flag, or it is sometimes also called as unsigned overflow flag. This flag is set to 1 when the results of unsigned addition the result the result as whenever doing the addition operation, the addition operation caused a carry, it has generated a carry, so then this flag is set to 1, and this is for unsigned operations. So that means to say a carry out has been generated from the MSB. So during unsigned operation, then the carry flag is set. So if this bit is 0, that means no carry has been generated. The next flag is V, stands for overflow flag, and sometimes it is also called as signed overflow flag. So this bit is useful in signed operations. So if this bit is 1, an assigned operation has resulted in carry or overflow. If this bit is 0, there is no signed overflow has taken place. So bit number 27 to 8 are reserved. So they are reserved for future usage. And then bit number 7 is stands for I, so which is IRQ disable bit or interrupt mask bit. So if this bit is 1, IRQ interrupts are disabled. If this bit is 0, IRQ interrupts are enabled. Similarly, the sixth bit in the CPSR stands for F, that is FIQ disable bit or FIQ mask bit. If this bit is 1, it disables the FIQ, fast interrupt request, and if it is 0, it enables the FIQs. The fifth bit in the CPSR is T bit, stands for thumb state bit. So ARM can enter into thumb mode or ARM mode. So if this bit is 1, ARM is in the thumb state, and if this bit is 0, it is in the ARM state. And last 5 bits of CPSR are meant for mode. So these bits tells the mode of the processor. So there are altogether 7 processing modes: user mode, FIQ mode, IIQ mode, supervisory mode, abort mode, undefined mode, and system mode. The processor enters into these modes whenever particular condition prevails. So let us study about modes. So the processor modes determines the register set which is active for particular mode, and also access rights to the CPSR. So how you can access the CPSR in these modes? All the modes are either privileged modes or non-privileged modes. A privileged mode will have full read and write access to the CPSR, while a non-privileged mode will only have read access to the control field but still have read-write access to the flags. So that means to say, in the non-privileged modes, we cannot write into control fields. Just we can read it, but we cannot write into the control fields. Control fields in the sense modes, IFT modes, that is interrupt mask bit, FIQ mask bit, and the thumb state and mode. So these you cannot change in the non-privileged mode, but you can, you still it allows to read and write access to the flags. So you can change the flags. The flags will be updated on the operations, but not these things. The mode and the IFT bits are not updated in the non-privileged modes. So I told there are 7 modes. So out of which 6 are privileged modes. So which are those? Abort, fast interrupt request, supervisory mode, system mode, and undefined modes. All these modes are privileged modes, and there is only one non-privileged mode, that is user mode. So processor enters into abort mode when there is a failed attempt to access a memory. Say this mode is invoked when you are trying to access a memory which you don't have permission to. For example, some memories are blocked from accessing, and if you try to access that memory, processor will invoke this mode. You are prohibited to enter into that particular memory block, and you are trying to access that memory, and will throw into this mode. FIQ mode stands for fast interrupt request mode. So these modes are generally used for transferring large amount of data between the processor and some peripherals. So these helps in faster movement of data, and it's one of the interrupt level, that is called as fast interrupt request. IRQ mode is entered whenever a peripheral wants a service from the processor. A peripheral or any hardware device needs service from the processor. It raises an interrupt, and once the interrupt is accepted by the processor enters into IRQ mode. The supervisory mode is this mode is invoked when operating system kernels are executed. So normally, whenever you restart your system, the processor will be in the supervisory mode. So because operating system kernels will be executing during that time, so hence the system will be there in the supervisory mode. Once it turns on completely, then the processor will be in the user mode. System mode. So system mode is a special version of user mode wherein it has a full access to CPSR. Full read and write access to the CPSR. It is nothing but a user mode, but it has a access to CPSR completely. And undefined mode is invoked when the processor encounters a undefined or not specified instructions. That means to say, if a processor encounters an instruction which is not defined in that particular machine, so it enters into undefined mode. It may happen because we may use the compiler, same compiler for different machines. So the compiler will not give a syntactical error because it is handled that compiler we are using it for same different processors. So that may directly enter into your system, and during that time undefined undefined mode is entered. So user mode is the one where program and applications are run. So these are the processor modes available in the ARM. So now this table lists all the modes. See, abort mode. So the for abort mode abbreviation is ABT. Is it a privilege? Yes, it is a privilege. And what is the mode fields? It is 10111. And next is fast interrupt request. What is the abbreviation? It is FIQ. Is it a privilege? Yes, it is a privilege. And what is the mode bit? So it is 10001. IRQ, that is interrupt request. IRQ is the abbreviation. It is privileged mode, and the mode bits are 10010. Supervisory, SVC is the abbreviation. It's a privileged mode 10011. System, SYS is the abbreviation. It is a privileged mode. 11111 is the mode fields. Undefined, UND is the abbreviation. Is the privilege? Yes, it is a privileged mode, and the mode bits are 11011. And user mode, USR is the abbreviation. It's not in a privileged mode, and the mode bits are 10000. So next, let's discuss one of the important concept in the ARM, that is bank registers. So I told there are 37 registers in the ARM, but not all the 37 registers are visible to the program all at once. So at any particular time, there are only up to 18, maximum 18 registers are visible to the program. Other registers are hidden to the programmer. So these hidden registers are called as bank registers. Each processor mode has got its own set of registers. So here in the user mode, we have got R0 to R15 and CPSR, and user mode and system mode. And in the FIQ mode, we have got separate set of registers, that is R8 FIQ, R9 FIQ, R10 FIQ, like that. So along with this user mode registers, it has got separate set of registers. So there are 37 registers in the register file. Of these, 20 are hidden at any different times. So these registers are bank registers. So and they have been abbreviated, or they have been denoted by the register number along with the postfix with the processor mode. That is, say for example, R13 of FIQ mode is represented as R13 underscore FIQ. All the modes can change by writing to the mode bits of CPSR, except user mode. So we can enter into other modes by writing into CPSR mode bits, but not into user mode. So we cannot come into user mode by writing into CPSR register. All the processor modes have set up bank register except system mode. So each processor has set up a bank register which are written at a particular time. They have separate set except system mode. All modes have got separate set of register. A bank registers maps one to one on the user mode register. So that means to say, so it maps one to one on the user mode registers. So here, if an system is changing from user mode to FIQ mode, R0 to R7 are used in the FIQ mode also. From R8 to R14, FIQ mode has got its own set. That is R8 FIQ, R9 FIQ, like that, R14 FIQ. So they maps one to one onto the user mode. That is R8 in the user mode is replaced by R8 in the FIQ. R9 in the FIQ is R9 in the user mode is replaced by R9 in the FIQ. Like that up to R14. And while going from user mode to FIQ mode, the CPSR content of user mode is copied into SPSR of FIQ. So that the environment of user mode needs to be retrieved while coming back to the user mode. So what all the flags are generated in the user mode needs to be preserved. That is preserved in the SPSR of particular mode. So that's what is maps one to one on the user mode. Suppose, say here an example is shown, that is the user processor is changing from user mode to interrupt request mode. So when it is doing so, it uses R0 to R12 from the user mode into IRQ mode also. But R13 of user mode is replaced by R13 of IRQ. R14 of user mode is replaced by R14 of IRQ, and the CPSR of user mode is copied into SPSR of IRQ, and the IRQ. So that means to say, in the IRQ mode, we cannot access R13 of user mode, R14 of user mode, and CPSR is common to all the processor modes. So that's what is bank. So now once the processor enters into IRQ, the R13 and R14 of user mode are banked. They are not visible to the user now because the processor is in the IRQ mode. When it is in the user mode, R13 IRQ, R14 IRQ, SPSR of IRQ are not visible to the user. So whenever processor enters into a particular mode, those set of registers will be visible to the user. So one last concept in the this chapter, that is pipeline. So pipeline is the mechanism by which we are executing instructions parallelly. They seems to be executed in the parallel. So an instruction execution is broken down into different works, and each hardware unit is assigned a particular work. Now here, the instruction execution work is divided into three parts. That is, one is fetch, decode, and execute. So this is a three-stage pipeline. So different processors have different stages of pipeline: 3 stage, 5 stage, 7 stage, like that. So a three-stage pipeline will have three operational units, that is fetch, decode, and execute. So fetch loads the instruction from the memory. Decode, it translates the instruction, it gets the meaning of that particular instruction and tells what needs to be done and generates the control signals. And execute instruction will process that instruction and stores the result back into the register. So for example, so here I have shown you three-stage pipelining. In the first cycle, add instruction is fetched. It has brought from the memory and placed into this pipeline. In the next cycle, add is moved into decode stage, and the next instruction after add is brought into the pipeline. The third cycle, add will move into the execution stage. Subtract instruction from fetch, it will move into decode stage, and the one more new instruction is brought into the pipeline, that is compare. So once the pipeline filled completely, it executes one instruction per cycle after that. So once the pipeline is filled completely, for every cycle an instruction is executed. If the pipeline is not there, it may take 2 or 3 cycles per instructions. But once a pipeline is used, for every cycle, one instruction completes its operations. So the one the initially it takes certain amount of time for filling this pipeline, because see, even initially for 3 cycles there is no output, so that is called as pipeline filling process. So what are the merits and the demerits of this pipeline? So pipelining increases the performance of the processor. Yes, of course, because for every cycle, once the pipeline is filled, for every next cycle, an instruction is executed. It reduces the amount of work done at each stage by increased pipelining. So if you increase the pipeline length, so say if I have a 5-stage pipeline, work done at each stage is reduced because I have to break the instruction again. So say for example in the execution stage I can make 2 blocks, that is execute, storing. So result storing is sent to for another next block, and execution is taken by one more block. So if you do like this, amount of work done at each stage is reduced in the increased pipeline length. So if the amount is reduced at each stage, again it increases the throughput. What are the demerits of pipelining? So it increases the system latency because it takes more cycles to fill in the pipeline before the processor can execute an instruction. That means to say, so that's what I already said in the previous example. So since it is a 3-stage pipelining, it is taking minimum 3 cycles to execute an instruction. So if the pipeline length is increased, it takes more number of cycles to execute in a single instruction. So that's what it increases the system latency. System latency here means from a processor is fetching the first instruction to it's giving the first output, executing the first instruction. So that can be, we can term it as a system latency. So if you increase the length of the pipeline, it increases the system latency. And one more demerit of pipelining is the pipeline can cause a data dependency. So data dependency means, so say I'll go back to the previous example. Suppose I am using a register in the first instruction is an add instruction. I am using say add R3, R1, R2. So that means say I am adding R1 and R2, placing the result in R3. And subtraction is in the subtraction, let's say subtract R4, R5. I am using totally different registers. And in the compare, if I am using the same register that are used in the previous instructions, so before the processor executes that instruction, if that is used in the next instruction, so it may give you an erroneous result because it's already in the pipeline, it's not been completely executed. You are using that register again. In such conditions, it may give you erroneous results. So that's what is data dependency. If you increase the pipeline length, so it can cause data dependency. So that means to say one stage of pipeline requires the data from the next stage of pipeline. So that's what is data dependency. And these are some characteristics of pipeline. So an instruction in the execution stage is processed only when the next instruction is brought in. That is to say, the instruction is executed only when the next instruction is brought into the system or pipeline. So second characteristic is PC will always point to an instruction address plus 8 bytes. So since ARM is a 32 bit, so here I am going back to the previous slide, that is here. So the address, let's say address of the PC is something, say 0x0008. So address of subtraction instruction will be 0x000C, and address of the comparison instruction will be 0x0012. So here, so uh, always PC will be pointing to the next executable instruction. So that means to say, once it is fetched, so PC is pointing to comparison instruction now, and add is being getting executed. So now PC is exactly pointing from add, so from the instruction add by 8 bytes, because each instruction is of 4 bytes. So now add is being executed, but the PC is pointing at comparison instruction. That means to say there are two places, there is sub instruction is there and comparison instruction. So it is pointing to 8 bytes from the instruction being executed. And in case of thumb, it is plus 4 bytes, because the instruction width is 16 bit. So the execution of branch instruction causes the ARM core to flush its pipelines. So what it means, say whenever processor encounters a branch instruction, so it comes to know it needs to be branched in the decode stage, and once it executes, it jumps to some other location. But before jumping, it has already brought some two instructions. One is there in the decode stage and another one is in the fetch stage. But once it jumps to some other different location, it has to bring the new instruction, and it has to execute those instructions. So what the ARM processor will do is, it will remove all the instructions which are it has brought before jumping, and start refilling the pipeline. So that's what is flushing the pipeline and refilling it. So ARM processor flushes its pipeline whenever it encounters a branch instruction. Now ARM10 uses a branch prediction, so which reduces the pipeline flush. So that means to say, R in the ARM10, it's a different version of ARM, so which uses some intellectual property, that is branch prediction. It predicts the branch before execution, thereby it reduces the pipeline, because it predicts the branching and it won't bring the next instruction, and it will jump to the branch and it reduces the pipeline flush. So an instruction in the execution stage will complete its execution even though an interrupt is raised. So the instruction in the execution stage, suppose an instruction is there in the execution stage, it has not completely executed, and there suddenly an interrupt has raised. So ARM will not stop what it is doing. That means to say, some instruction there in the execution stage, so it will complete that execution. Only after completion it will jump to the interrupt. Other instruction in the pattern will be abandoned, and the processor starts filling the instruction from the instruction handler or the vector table. So that's what we have to study in the first chapter. So thank you.